Okay.
There we go.
Okay. Everybody, welcome to our IFS seminar, number 17, if I'm not mistaken. We have today Dmitri Bykov, who I had pleasure to work with in Potsdam, and he's currently in Moscow. He will be talking about sigma models in 2 dimensions, right?
Yes.
Okay, please.
Okay, thank you very much for the invitation. Yeah, I will be talking about 2-dimensional sigma models. More exactly, there is a certain equivalence between what is known as Gross-Neveu models and sigma models. So there is some equivalence, some class of particular, it includes the so-called CPN model and many others.
Tima, sorry to interrupt. We encourage discussion here usually, so if you don't mind, we will ask questions during the talk, or if you prefer, you can make some pauses at some point for questions.
No, you can ask during the talk. Just the question is, I mean, people know what are sigma models and so on. Or
maybe better to start with the definition.
Okay. So just first teaser. 2-dimensional sigma models versus also 2-dimensional some other class of models called Gross-Neveu models. And these are, you could think of these as the phi to the 4 theory in 2 dimensions. So this is why it's useful. I think it's a useful correspondence because this is supposedly complicated. And this is somewhat easier, or at least many of the complications are resolved. So, okay, so 2-dimensional sigma models are 2-dimensional theories. So that means that describing some maps from 2-dimensional manifold or Riemann surface sigma 2 to a target space M. And on the space of such maps, there is a Lagrangian, and also the action functional that we are supposed to minimize. So these maps are supposed to satisfy some differential equations. Yes. So in the simplest case, the action is d to z. G here is X are the maps. Z is the coordinate on sigma 2, so there is coordinate z bar. It's a Riemann surface. And then we have some maps to a target space M with coordinates X, right? Or, well, it's kind of tautological. So either coordinates are called X or the maps are called X. And on the space of such maps, there is this action. Alpha goes from 1 to 2. So these are the 2-dimensional coordinates on the world sheet. So this is called the world sheet. This is called the target space. Actually, for most of my talk, I will only be concerned with the case that sigma 2 is whatever the simplest possible examples, which are, well, you could either think of C or maybe sometimes a sphere, CP1. So yeah, mostly C, basically, just with some decay conditions at infinity. But in principle, yes, they could be, say, cylinder, then whatever Riemann surface with handles and so on. That's kind of left for the future. So this is called a Dirichlet functional, Dirichlet energy functional. And well, it's not the only action that you can write, so you can add some other terms, symmetric fields on the target. So yeah, so G is the metric on M, metric on M, on the target space. And yeah, that's not the most general thing you can write. So in practice, we deal with more complicated stuff, maybe some extra fields and so on, but this term is always present. Well, so in principle, one would be interested to construct the quantum theory of such maps, if you like. So compute some partition function, which roughly speaking is we integrate over dx e to the minus. So this is this is kind of symbolic, this path integral.
Sorry to interrupt. This manifold M is a complex manifold, right? If I understand it correctly, and the maps X are assumed to be complex holomorphic or so?
No. So in general, in principle, M is not necessarily complex, although it's true that in my class of models, they're complex. So, but
and
here,
the maps X are not supposed to be holomorphic?
No, they're not holomorphic, so they are harmonic, what is called harmonic maps. So the sigma models is equivalent to the, well, at least classical. Classically, this is the theory of harmonic maps. So you can see from the action, right? If you have if M is just R, then your equation of motion is just Laplacian of X is 0, right? So it's not necessarily, well, you could of course take C, it will still be, you could take MC.
I was only wondering why the complex structure on sigma manifold is relevant. Why just not take any kind of manifold? Why especially complex if that complex structure isn't being essentially used? Yeah.
Yeah, it will be essentially used. Yeah. So far that I've written it, it hasn't been used. Yes, you could just take a Riemann surface or two-dimensional manifold. But yeah. Well, it's true that harmonic maps, I mean, holomorphic maps do play a role. So the holomorphic maps are instantons in this theory. So, yeah, so they are a subclass. Harmonic maps. And these are instantons. Yeah. So to define them, yes, you would have to pick a complex structure, and you can write some kind of what is called as Bogomolny inequality on this S, or in math it's called Wirtinger inequality. Yeah, say this is yeah. So far, it's not needed, but yeah, I guess it will be needed. Yeah, one other reason that we want a complex structure is that we actually want to write the action in complex coordinates. I mean, in conformal coordinates. So in principle, we could imagine that this sigma is equipped with a metric, right? And then S would be replaced by So actually, maybe that's the most natural setup where we have a metric both on the target space and on the worldsheet.
But then if there is a complex structure on sigma, do you take gamma to be a Hermitian metric, or do you consider it as a real Riemannian manifold?
No, yeah, it's that's the point. So on a so this is a wild invariant combination of the metric, right? So this is invariant with respect to so actually only the conformal class of metrics matters. And then there is a statement that conformal classes of metrics are equivalent to complex structures in 2 dimensions. And the equivalence goes by putting the metric in conformal form. So so you should put the that was the alpha. Well, z maybe is not a good notation here. Dx alpha, dx beta. These are small x's. You bring them to the form that it's omega times dz bar.
Yeah, but then gamma should be a Hermitian metric in order that you operate with the holomorphic coordinates, local coordinates, right? Z bar.
No. I mean, in 2 dimensions, you can always bring it to this form. So every metric is Hermitian in some complex structure, and that's the equivalence between conformal classes of metrics and complex structures.
Yeah, but the difference is the Hermitian metric also encodes a symplectic structure aside from a real. Its real part is a Riemannian metric, right? And its imaginary part is a symplectic form.
Yeah.
And then when you don't consider the symplectic form, then you don't get an invariant complex geometrical object. So in order that you can contract with complex holonomic indices, you'll have to take the full Hermitian matrix, don't you?
Well, I mean, I think here the symplectic structure is irrelevant because it's just the volume form. So it's somehow determined by the metric.
Okay, you can think of it that way. Yeah, there is a unique symplectic structure. That's right.
Yeah. Yeah. So so here I will always work in this conformal coordinate. So ZZ bar, because then you see the omega factor just drops out of this combination, because this is invariant with respect to scalings. And so kind of effectively you have a flat metric entering the action. So
sorry, but could you do that on quantum level, only just classically?
Yeah, this is classical. I mean, there is a wild anomaly, right? So you have to.
Yeah.
This is what in string theory people worry about. But like I say, in principle, I just assume that my worldsheet is just C for the moment. So here, such a problem does not arise. So.
Okay.
Yeah. Erase the factor of 1/2. Then there is a union. Yeah. So. Okay, so anyway, the point is that well, this is a 2-dimensional generalization of well, 1-dimensional theory as to one-dimensional theory in 1D. The same setup. This gives you just a mechanical particle. On M. the same Lagrangian. I mean, if you just do dimensional reduction to 1D, and this describes a mechanical particle on M, or which this is equivalent to geodesic flow on M. There is this well-known map that instead of considering geodesic flow, you can just consider particle-like Lagrangian with L equals M V squared over 2. So the quantization of this gives quantum mechanics on M. So quantization. In particular, the Hamiltonian is minus the Laplace-Beltrami operator on M. So this is the quantum theory in one-dimensional case. So the theory of sigma models kind of asks whether it's possible to do something similar in 2 dimensions. And that's more complicated because it's a quantum field theory. So what I want to do here is I want to claim that for a certain class of models, you can do this mapping to Gross-Neveu models, which are easier because they are polynomial models, basically. Here, the problems come from the fact, I mean, in the sigma model setup, the problems come from the fact that there is this dependence on X in the metric. It could be, in principle, arbitrary dependence. Then the quantization will heavily depend on which coordinates you use to quantize it, and so on and so forth. So the Gross-Neveu formalism resolves partly some of that stuff. So let me write the Gross-Neveu Lagrangian. You consider following Lagrangian. So sum bar A kappa so this is the Gross-Neveu Lagrangian. So psi is a collection of fields which are Dirac spinors, so to speak, in two dimensions. They can be split. These are fields with 2 components, so they can be split as UA, VA bar. Now U and V are just single, functions. Single functions. So psi is a column vector with 2 components, U and V bar. And psi bar is just Hermitian conjugate. 1 plus sigma 3, these are just projectors of the type 1, 0, 0. And these are 0, 0, 0, 1. So kappa is a coupling constant. The fact that there are these projectors, these are called chiral projectors. So the model is called chiral Gross-Neveu model. Chiral. And D is a U1 covariant derivative. Gamma mu, D mu, gamma mu. Mu runs from 1 to 2. So this is 2 dimensions. So is it clear? Yes.
Sorry, Dima, I just would like to understand what we are doing. What you want to tell us? Just what the main task or main result or something?
Yeah, the main task is that this model, the sigma model here, is equivalent to this Gross-Neveu model here. And the claim is that this simplifies, well, using the Gross-Neveu model simplifies the calculations and so on, and well, gives a different take on the.
Yeah, but in 2 dimensions, everything is equivalent. If you will bosonize fermionic variables or fermionize, and I think this is a new result which you.
Yeah, it's a new result. Moreover, I'm not bosonizing or fermionizing anything. I mean, this will be a Gross-Neveu model with bosonic fields. Psi I are commuting variables.
Okay.
And I mean, I wouldn't go so far as to say that everything is equivalent. I mean, you could imagine. I mean,
no, just I'm an old guy, so I remember that Gross-Neveu model equivalent to some bosonic model. I'm not sure to which one, but anyway, even interacting model, yeah, with psi4 interaction, also equivalent to some other bosonic sigma model. I think so, yeah, or not?
I don't think it's equivalent to sigma. I mean, there is the equivalent to the massive steering model and Chang-Gordon.
Yeah, for example, yeah. So this is not the similar things or something completely other, orthogonal to that?
Completely orthogonal to that, yes.
Okay.
Yeah. So,
so Dima, you would say that you are, this is a first order formulation for the other theory. I mean,
yeah, that's right. This is,
should we understand, sorry, Dima, that roughly speaking, this Gross-Neveu model is first order is just sigma model rewrite it in first order formalism.
Well, yes. So there are several points.
This U and V, U is probably parameterized CPN or this complex scalar manifold, and momentum is some combination of U and V, right? Am I right?
Momentum is V. Yeah, V is momentum. So
V is momentum. So, okay, understand. So it is just first order formalism in light cone, probably, right?
Yes, you can say so. Yes, that's right. So there are several things. So it's first order formulation, like you say, first order formulation.
Just to fix something, so it means that momenta and coordinate you unify in one psi field, yeah, and then write symplectic form, and then you have Gross-Neveu model for first order formalism of your bosonic sigma model, yeah, or not?
Yeah, that's right. But the funny thing is that what matters here is a complex symplectic form.
Yeah, okay, that's another story. Okay, thank you.
Yeah, but yes, that's correct. So the first term could be interpreted as a Poincaré-Liouville form. I will now rewrite it in UV coordinates, so it will be more clear. So Poincaré-Liouville form, theta, such that its derivative is omega, the symplectic form. So yeah, it's a first order formulation plus the fact that you should be using, so you write everything in homogeneous coordinates. So you write CPN as a CN minus 0 divided by C star.
Roughly speaking, it is Legendre transformation with respect to Z variable. And by this reason, complex structure is essential here.
Yeah.
This sigma, the fact that you have Z and Z bar allows to perform just directly this Legendre transformation with respect to complex variable, right? Am I right?
Right. Yes. Well, I will show now that yes. Well, it's you also drop some topological term when you do this. So, but yes, that's almost exactly correct. So I use first order formulation, and this Cn minus 0 divided by C star. So C star, so the U1 gauge field. So U1 gauge field is promoted to C star.
Mm-hmm.
And I will explain that it involves chiral symmetry. So this involves chiral symmetry. So gauging chiral symmetry. Yeah, this is also what is called in the context of sigma models. This is called GLSM, so gauged linear sigma models. GLSM.
So when you say chiral symmetry, what exactly do you mean?
Yeah, so chiral in the same sense as here, we called it the chiral model, right? So I said there are these chiral projectors here. It's all sigma 3, this thing. So it becomes more clear if we rewrite the Lagrangian in the U and V variables. So in the U and V variables, one just gets VA V bar UA plus VA bar D U bar, maybe up to a total derivative, which I integrate by parts somewhere. But, plus kappa sum of UA squared this is Lagrangian. So chiral symmetry means we multiply U by lambda U and V so lambda is an arbitrary complex number, non-zero.
So this means that you restrict yourself to complex projective space. But this means the restriction of target space to CPN.
Well, in principle, yes. So far, I haven't said that I gauge this symmetry. So just Karapet just asked what it is. So I'm just saying it is this symmetry, yes. Then I do gauge this symmetry. That's right. And then I restrict to complex projective space, yes.
May I ask some other question? You notice at the first transparency that sigma worldsheet could have a non-trivial topology. Why it is important? Because in all these things, I don't see any how to say any reference to non-trivial topology of sigma.
Because well, because these gauge fields, they can be non-trivial on worldsheets of non-trivial topology. So, for example, they can have non-zero first Chern class. They can have holonomies around various cycles. So that's the main reason. So also
when you perform, okay.
Yeah.
No. Now clear.
Also, in the context of integrable models, the most kind of reasonable setup is when you have a cylinder. Actually, this is the most well-studied setup. Is when you have a cylinder. So you have some time. This is time, and then you have a finite volume kind of.
My question is the following: when you perform this Legendre transformation with respect to that variable, how is this topology? Do you have take into account this non-trivial topology of worldsheet or
not? Yes. So. Well, it's better not to think of it as a Legendre transformation. Let's just look at this Lagrangian. Yeah. So on a worldsheet of non-trivial topology, as you say, you see this V and U This part is what is called a beta gamma system. You could say that so UA is a section of some line bundle L over sigma, and V is a section of a dual. Dual means that L prime is a canonical bundle times L inverse. So then it starts to matter which line bundles you take, and this kind of becomes an additional data of your theory. So in situation of trivial topology, you have just trivial bundles. So that's maybe the way to think about it. I'm saying that on a worldsheet of non-trivial topologies, maybe better to take this Lagrangian as the defining your theory. So the benefit of looking at it this way is that now U and V are not coordinates on projective space, right? They're just some linear coordinates, sections of some line bundle.
No, sorry, it's my actual you predict my question. So V is not momentum conjugated to U in the sense that V and U form not cotangent bundle of CPN, but something different. Am I right?
Well, yeah. So, well, morally, it's the cotangent bundle to CPN, but it's true that when you, it's something. Well, you see, formally speaking, this is a T star of CN, symplectic reduction by C star.
Oh, but it is the same actually. You will get that some twisted CPN.
No, I mean when you do the symplectic reduction, you should say that U is not identically zero. So
you will get some system with some additional term, magnetic field, roughly speaking, with constant magnetic field.
No, there's no constant magnetic field. I mean this is complex symplectic reduction, right?
Sorry, when you rewrite CPN in homogeneous coordinates, this means that you reduce Cn plus 1 by U1, and you get CPN rewrite in homogeneous coordinates.
Yes.
When you perform, roughly speaking, U1 reduction of T star CPN, Cn plus 1, you get some CPN, T CPN, with twisted, equipped with twisted symplectic structure, corresponding to some external field, magnetic field, or if you want.
Well, I'm sure you can add a magnetic field here, yes. I mean, but adding magnetic field would be, you would have to add a term, something like zeta A bar here.
Well, it will appear automatically when you will rewrite this system in terms of inhomogeneous coordinates. That's my point.
No, it will not appear automatically. I mean, I think the question that you made is what I wrote here. So you're asking, I'm saying that at face value, I have this quotient, T star Cn by C star, complex symplectic reduction. Now, the question is this equivalent to T star of CPN minus 1? I'm saying this is almost equivalent, but you should put here some on the one hand this is symplectic reduction, on the other hand this is like GAT quotient, right?
You should add some additional constraint.
Yeah, well,
and you will get TCPN with twisted symplectic structure.
Well, I don't know why you want twisted, but I mean
twisted symplectic structure is canonical plus external magnetic field.
No, I mean, okay. So I'm saying there's no additional constraint. It's just you put something like stable points or something like this. So you exclude you exclude the points where all UA are 0, right? You just require that not all UA are 0, and then if you take the symplectic reduction of that subset, then this will give you a T star of CPN -1. Well, about twisted magnetic field, I don't think there's any twisted magnetic field. I mean, I can just directly show you what you get out of this construction, right? So you take this Lagrangian here, and let us exclude the V variable. Let us go to second order formalism, right? Or okay, yeah, let's go to second order formalism. We can also discuss the first order formalism. So then you get L equals 1 over kappa, sum over V bar UA. And this is basically the CPN sigma model.
Okay.
This is a gauge invariant with respect to U goes to lambda or ZZ bar. So this is a C star gauge invariant. By the way, the non-trivial point here was that we actually had a kind of usual Dirac system with a free fermion, albeit a commuting one. So we had a U1 covariant derivative, but it's automatically a C star covariant derivative. So in these two-dimensional systems, the gauge field can be promoted to it automatically gauges U1 and an additional R star, which are combined into C star. So when we want to impose the condition that we gauge C star here. So we are gauging chiral symmetry. That's what I want to say. Anyway, so the Lagrangian, when you integrate over this momenta V, you get back to the geometric form of the Lagrangian. This is using this C star symmetry, you can set a partial gauge. And then you get rid of the denominator here. And then the Lagrangian is the Lagrangian of the action. This is the integral of the Lagrangian. This is the Lagrangian of the CPN model plus a topological term. It's the integral. So at least classically, these are equivalent systems. You could, of course, instead of picking this gauge, you could pass to inhomogeneous coordinates. This would be a different gauge. And then you get the action in the inhomogeneous coordinates. Yeah. You could also pass to inhomogeneous coordinates at the level of the Lagrangian. So if you want to look at the symplectic form, you can look at the Lagrangian. And variation with respect to the gauge field gives you a constraint, right? The moment map constraint. So variation. Now you could set UN equals to 1. This is the gauge. And then from the constraints, you find that Vn is minus some Vb ub b from 1 to n minus 1.
Mm-hmm.
And then you substitute this into the Lagrangian, and that's it. So I do not see any additional magnetic field. I mean,
okay. Let me interrupt you. Magnetic field will appear. It is not necessary to put V on U is equal to 0. It could be equal to some constant, and constant will correspond to magnitude of magnetic field.
Yeah, that's right. That's what I wrote before, right? I wrote here that you can add this term to the. This will give you a zeta. This is like Payelopoulos's term in this language.
Yes, precisely.
You could put a zeta here, and zeta would have to be integer.
Yes.
And this would be a flux of the.
And this is monopole charge, roughly speaking.
Yeah, exactly. Yes, that's right. Okay. Anyway, so far I explained that there's an equivalence between this fourth order system, the Gross-Neveu system, and the sigma model. So one, you might wonder what one can do. Well, one still has the gauge field, right? And it seems to be somewhat problematic. But the gauge field is an auxiliary gauge field. So we have to integrate over it in the path integral, so to speak. It's a dynamical auxiliary gauge field. And its gauge transformations is A bar goes to A bar plus I d bar log lambda. So lambda is a complex valued function. So in particular, we can actually pick a gauge where it's exactly 0. Okay. So we said that A bar mu equals A bar plus I d bar log lambda equals 0. This just involves solving the equation that log lambda is this Cauchy-Green formula, log lambda of ZZ bar d2w Okay, so I can explicitly solve this equation and set A bar to 0. And also A. A is the complex conjugate to A bar. So the gauge is A bar equals 0. So in general, the point is that, this formalism with this auxiliary gauge field is like a gauge analog of string sigma model. So in string sigma model, you have a metric as your gauge field, so to speak. And you can bring the metric to a conformal form. So you can use conformal gauge, where all components drop out if there is no Weil anomaly. So this is the analog of conformal gauge. And the inhomogeneous, when we were choosing inhomogeneous coordinates, UN equals 1, this was the analog of light cone gauge. So also notice that actually this gauge transformation, this complexified gauge transformation, means that we cannot add any local field strength densities to the Lagrangian. There's no local gauge invariance. So we cannot add a term like F mu squared. Because, well, FZZ bar in this case, FZZ bar is not gauge invariant. with respect to the C star gauge transformations. So A is really a topological. So the gauge field is topological. So what this approach gives you is that it shows you that the gauge field is topological, can be eliminated, as opposed to the old approaches where one always worked on the gauge UN squared equals 1, this gauge, where C star is already reduced to U1. And you cannot eliminate the gauge field in that sense, and you have this quadratic constraint. Here, I don't have any quadratic constraints. I just have this system, right? Where additionally, I can even set the gauge field to 0. So I have an ungauged Gross-Neveu model. And in particular, you can develop a well-defined perturbation theory with respect to kappa. So again, in usual sigma models, there's no well-defined perturbation theory, SUN invariant, so, or whatever symmetry group invariant perturbation theory, because what one usually does is one has to solve the constraint, one solves the constraint. So the standard constraint is this constraint, and one would have to solve it, means that one restricts to a neighborhood of some point in the target space. And this gives an infinite number of interactions, and besides, it breaks the symmetry. So here, we just have a quartic interaction. That's all we have. And symmetry is not broken. It's SUN invariant perturbation theory. The propagator is just 1 over Z, right? So this is, say, U, V. This is just 1 over Z, the propagator. And you have some vertex, some quartic vertex. Again, there are some arrows. And then, well, of course, there's 1 over Z bar also. I mean, this is 1 over Z, this is 1 over Z bar. Yeah, you have to draw it with colors, but anyway, that's the point. Now, this whole thing can be generalized. So the first thing we want to insist on is that this gauge symmetry is anomaly free, right? Because we heavily use it to pass between these various gauges. And there is some anomaly cancellation condition. So the gauge symmetry C star should be anomaly free. This is a Wheaton type cancellation condition. It says that the super trace of a product of 2 generators should be 0 in your representation W, in which U variables live. So this means that the bosonic model has an anomaly, because in the bosonic model, the super trace of the generator, square of the generator is n, is not 0. So you'd have to add fermions to the model. This can be done in many ways. So in particular, maybe particularly interesting is the supersymmetric case. But there are other ways. So the basic idea is the following. So you consider this L0, this Lagrangian, whatever free Lagrangian you have, say like what I was writing, VA D bar UA, let's say the holomorphic part. Plus a fermionic completion, which we will call BA D bar CA. These are our anti-commuting variables. And then you this part of the Lagrangian has GLN/N symmetry group that rotates the U and C variables and V and B variables. So now you pick a subgroup G of this GLN/N, and you construct a Noether current for this group G, or this symmetry G. So Noether current J JA of Z bar. So this lives in the Lie algebra of G. In the free system, it's a holomorphic current. And now what you do is you couple, you say that your full Lagrangian is your L holomorphic plus L anti-holomorphic plus kappa trace JJ bar. Okay, and this will be your interacting system. This is a generalization of this Lagrangian, this Gross-Neveu Lagrangian that I showed here. So I mean, this second term here also can be written as trace JJ bar. If you say that J is U times V. Okay, but the general setup is useful, for example, to construct a supersymmetric generalization. So in supersymmetric, so if you want to have a supersymmetric thing, you say that J is U times V minus B times C. And then, well, it's a statement that you have to prove that it's supersymmetric, and so on and so forth. So you plug this in here. You can kill the gauge fields again. And what this is a perturbation of a free conformal field theory by an operator. And J is a Kac-Moody current of your free conformal field theory. And the interesting thing is that it's a current at level 0. So we know that Kac-Moody currents satisfy a operator algebra, right? So there's something like DAB K plus FABC KC. So K is the level. Oops. Okay. So K is the level. Okay, it got deleted for some reason. Okay. So, I mean, so the Lagrangian is, or maybe I should write the X.
It wasn't saved.
Yeah, it wasn't saved. Yeah, there's some bug. I mean, this is kappa. And yeah, so this JA of Z, JB of omega, A delta AB. Well, we only care about this term anyway. So this is a level of the Kac-Moody algebra. And it can be computed from the 2-point function. So you compute the 2-point function, and you find out it's 0. This is because, well, in my case, J equals U times V minus B times C. So the bosonic piece cancels the fermionic contribution to this thing, and it's 0. So it's a level 0 Kac-Moody current. So the statement in this case is that on the one hand, you have a supersymmetric CPN sigma model. On the other hand, you have this kind of perturbation of conformal theory, conformal field theory by a current interaction where the current is taken at level 0. Okay, this should be an equivalence. Well, these systems, like perturbations of conformal field theories, have been studied without relation to sigma models, just have been studied abstractly. And there is actually a conjecture for the all-loop beta function of this coupling kappa. So there is a conjecture.
The kappa is not the same as what is in the two-point function, right? Like in the current.
There's k. Yeah, I mean, the kappa is the coupling constant. K is the level. It's an integer. So yes. So there's a conjecture for the all-loop beta function, which says that beta kappa is it's minus C2 kappa squared 1 plus 1/2 k kappa squared. So C2 is the second Casimir. So adjoint representation Casimir of our symmetry group, so of G. So in the case of SUN, C2 is N. And the point is that if we substitute here k equals 0, there's no denominator. So this should correspond to the supersymmetric case. So that means that the beta function is one loop exact. And this seems to match the known results about supersymmetric sigma models. So the supersymmetric CPN models, beta function from superspace analysis, beta function is one loop exact. But I mean, this formula, if it's correct, it's a conjecture, like I say, it gives a beta function of a much wider class of sigma models and so on. And it would be useful to obtain it directly from the Gross-Neveu setup. So this is a beta function of the Gross-Neveu model. So this is the Gross-Neveu model beta function. And by this equivalence that I explained, it should match the sigma model beta function. Okay, maybe, I mean, this is, well, there's many things I could talk about, but I mean, I guess I should wrap it up, right? I mean,
yeah, I mean, we started a bit late, so maybe a few more minutes if you have to conclude.
Yeah, I mean, well, there's also the story about Riemann surfaces. Like I say, that on Riemann surfaces, you cannot set the A equals A bar equals 0. You would have some moduli remaining. And these are moduli, so these are moduli of gauge fields modular complexified gauge transformations. So in math, these are known as moduli of holomorphic vector bundles. Vector bundles over sigma. And then there is this well-known theorem of Narasimhan and Seshadri that says that it's related to representations of the, so it's related to flat connections. And to representations of the unitary representations of pi1 of sigma to the your whatever SUN or your symmetry group. So like in string theory, you integrate over moduli of complex structures or moduli of metrics. Here you can in principle set up a similar perturbation theory where you integrate over moduli of flat connections or moduli of holomorphic vector bundles. Yeah, you would in general have to well, here you would have to fix the genus of your surface, so you don't sum over genera. You fix the genus, you fix your Riemann surface, but you sum over first chain classes of your vector bundle. So the first chain class is an integer, and you sum over all first chain classes. This is the same as summing over all instanton numbers in the language of the sigma model. And for each value of Chern class, you have a moduli of well, flat connections or central connections, what is called. So some well-known moduli space. Yeah, and maybe I should also mention that these models are also, well, believed to be integrable. One main reason for this is that when you consider this action, the equation of motion for the current J is just d bar J equals kappa commutator of J bar. So these are principal chiral model equations for motion. Which is known to be integrable. So these models are kind of sub models of the principal chiral model in some sense. So integrability comes from this fact. So you can just derive it explicitly from the equations of motion. That's the derivative of the current. So you see, if kappa is 0, this would be the holomorphic current of the free system. But if kappa is non-zero, this is principal chiral model, subclass of principal chiral model. And yes, I hope it was clear, but kappa is related to the radius of the target space as 1 over r squared. So small kappa is large radius, small curvature. So this is the usual curvature expansion of the sigma model. Okay, so
flat target space would correspond to chiral currents.
Well, flat target space maybe is not a good example, but I mean a flat beta gamma system. I mean the free beta gamma system corresponds to flat to holomorphic currents.
So you have to define what was the beta gamma system.
Like the free fermion. I mean this this theory, like the free fermion. This piece is a beta gamma system.
Oh, okay.
So it's like a free fermion, just that first of all the variables can be commuting, not necessarily anti-commuting, and also they can carry different spins. So fermion carries spin 1/2, 1/2. But you could say that, V has spin 2 and U has spin -1 or different spins. So this would make it different from the fermion thing. But
beta gamma, it's not like ghost action string.
Yeah, like a ghost action and string, yes. So beta gamma or BC system, yes. So this is also the reason why when I was writing the supersymmetric case, I was using these BC variables. Where was it? I think it got deleted during the process. But I mean, I was starting with the action L0, which was VA E bar UA plus BA E bar CA.
Okay.
So this is like a BC system, yeah. In string theory, this is what's called beta gamma. So beta gamma usually refers to the commuting variables, but it's not a big deal in either use. These are also called symplectic bosons, actually, in conformal field theory. Symplectic boson. This kind of action, bosonic action that looks like fermionic action. So yeah, I mean, so basically, I kind of outlined the whole thing. The general idea is to understand integrability from the point of view of this Gross-Neveu model, for which, like I say, you can build a well-defined perturbation theory and so on. So the goal is to formulate integrability in these terms, integrability of these models, and then maybe to extend it to other Riemann surfaces and so on and so forth. This also works. All of this also works for SO, SP, P sigma models. So it's not only CPN model. It's SO, SP Grossmannians, for example, can be formulated in this way. Yeah. It's also useful at the level of quantum mechanics. I mean, you can effectively solve quantum mechanics also with monopole fields, like was mentioned. You can naturally introduce monopole fields here. So there are various lines of development. I just kind of outlined the main idea. Yeah, I'll be happy to answer if there are more questions.
Yeah, let's officially thank you for the talk and then start the question session. So,
I thought it was an hour ago, but okay.
Yeah. So I will start with a question from the last statement you made. I mean, it's a bit to the side, but okay, you said you can essentially solve quantum mechanics with the monopole fields. Can you expand on that? I don't completely understand what you mean by that. And what do you mean by monopole fields?
Monopole field. Well, you can view quantum mechanics as a so consider a mechanical particle, just particle on CPN.
Mm-hmm.
Then you write Lagrangian, which is 1/2 some usual metric. You put a CPN metric here, but then plus you can add a AI xi dot, a magnetic field.
Mm-hmm.
So there is on CPN there is an SUN invariant way of constructing a magnetic field. So I mean everywhere we require SUN invariance, right? So on the, for example, on a sphere, this is a kind of hedgehog magnetic field.
Mm-hmm.
It's rotation invariant, and it corresponds to kind of as if there was a monopole in the center of this thing, producing this flux. So the same thing can be done on CPN for any n.
Mm-hmm.
Now, if you quantize this thing, quantize. Without magnetic field, like I said, you get a Hamiltonian is minus the Laplacian on your, depending on your metric. So this is without magnetic field. So with magnetic field, you get a generalized Laplacian. So it's called also Bochner Laplacian. Bochner Laplacian. You can also do this in a super symmetric setup. Then you get some Laplacian, which is a square of a Dirac operator. So n equals 2 supersymmetry. You get your Hamiltonian is minus the square of the Dirac operator in a magnetic field on CPN -1. So you can solve all the systems and using this approach, like it was correctly mentioned. So so you see this constraint we have. So V and U are canonical variables, right, in quantum mechanics. So V is a derivative with respect to U. So zeta is this flux of a magnetic monopole flux. So suppose there is no magnetic monopole, then you take this constraint and you say that upon quantization, the constraint becomes UA d over dUA. Right? This means that your wave function is homogeneous.
Mm-hmm.
So wave function is homogeneous. In UA.
Mm-hmm.
So that means it's a function on projective space on CPN -1. So that's a correct kind of constraint that ensures that your wave functions live on the correct space.
Mm-hmm.
If you basically if you put some integer here k, and you have an additional constraint for the barred variables. -k. Then this means that your wave function is multiplied by a phase. If you scale all UA as e to the phi, your wave function psi, which satisfies these constraints, scales like e to the I phi k. This means it's a section of some line bundle over your CPN. This is what monopole does. I mean, it says that your wave function is a section of a Hopf bundle, power of the Hopf bundle over CPN. But anyway, I mean, you can solve all of this. So we actually have an upcoming paper with a Smil guy where we will discuss this for CPN. But this can also be done in all kind of systems of this type. Yeah, so the monopole means you add this monopole term without breaking SUN invariance.
So, thanks. Coming back to your general statement about equivalence of the two systems. So, Gross-Neveu model equivalence to the sigma model that you showed in the clinic. So it looked as if one just does some sort of first order formulation, but it's not exactly that, right? It's not so straightforward to show this equivalence. So like, can you make a more concrete statement? What is equivalent to what in these two systems? So the x is in this variables of the sigma model can be written as some bilinears of the U and V in the Gross-Neveu model, or
no. So the x's are the u's. So so first I just said that x are real coordinates, yes. Then we restrict to complex target spaces, such as CPN.
Yeah,
you can choose complex and holomorphic, anti-holomorphic coordinates, right? U and U bar.
Okay.
So U and U bar are the U and U bar of the target space, right? This is clear from this expression here. And the V are the momenta. So when you solve for V, you vary this Lagrangian with respect to V.
Yeah, so you get this one that is given only through U.
Yeah, you get the V bar UA equals kappa modulus U.
And this is not equivalent to the starting one, right? The sigma model, because you have here this. I mean, I don't see the target space metric here.
The metric arises from the gauge field, yes. So I mean, it's a GLSM, right? So so you integrate over V, you get this Lagrangian. It already looks a bit like sigma modular Lagrangian, right?
Yeah.
So if you want to have an explicit Fubini-Study metric, you take variation with respect to A, the gauge connection, and you exclude A. A enters algebraically, right? A just stands in the covariant derivatives. So when you take variation with respect to A, you get a linear equation for A, which you solve, and then you plug it back into the action, and that's equivalent to having a metric, curved metric.
How do you, I mean, you didn't write that part. How do you solve for the gauge field? So I don't completely see how does the metric arise in this case.
Yeah, I mean, for example, let's take a variation with respect to A bar, yes? So then I get what remains is just the sum over UA d UA bar equals 0.
Okay.
and d UA bar is d UA bar plus I A UA bar.
Yeah. Mm-hmm.
So then you solve this, and you get that I A equals I sum over UA d UA bar over sum over UB squared.
So A is just the U1 connection here.
Yeah, C star.
Okay. Now where do you see the metric coming in again? I'm a bit confused.
So this thing becomes the Lagrangian schematically written as follows. So it's L equals 1 over kappa G I J bar D U A. So I mean D U I. Maybe I should use A B bar D U A D bar U B bar. Right? G is the metric.
I mean, but from what you started from this Gross-Neveu model, integrating out A, you will not get arbitrary G, right? You get something very specific.
Yeah, of course. I get the CPM, the Fubini-Study metric. So more exactly, I can write it explicitly, right? It's like 1 over U squared delta AB bar minus UA bar UB, like this.
And
this is the first piece that was kind of present, and this comes from the gauge field.
Yeah, so this metric is not how to say, it's degenerate, right?
Is degenerate, yes, because this is this is using homogeneous coordinates.
Okay.
So there is a C star gauge freedom. That's why it's.
But the statement of equivalence to sigma model was phrased. I misunderstood then. I thought it's a generic sigma model with arbitrary target metric.
No. It's not so generic. No. It's a class of models. So generally the idea is the class of models related to quiver varieties. So the phase space, which is the kind of the phase space should be a quiver or maybe super quiver variety. Quiver variety means there are some nodes. For example, this is a quiver for a flag manifold. So so this is a phase space of Gross-Neveu model. So if the quiver variety, let's call it Q, if Q is a cotangent bundle of something, then this is equivalent to a sigma model on M. So M becomes the configuration space or the target space of your sigma model. So yeah, so quiver varieties are very special special varieties and so on and so forth. For example, there's also an interesting relation to nilpotent orbits. So it's known that there are some so nilpotent orbits in complex Lie algebras. They can be described as quiver varieties. On the other hand, it's known that the nilpotent orbits are singular complex varieties, complex symplectic varieties. But it's known that the resolutions of these guys, if they exist, so in the cases when they exist, resolutions give cotangent bundles of some homogeneous spaces. So the claim is that these are, what I'm getting in this construction is these homogeneous spaces are the target spaces of the sigma models. So that's the relation between so quiver varieties. This is the Gross-Neveu side, and this is the sigma model side. So if you want to have a sigma model with G over H target space, you should find an nilpotent orbit whose resolution it is. And then for this nilpotent orbit, find the corresponding quiver formulation and write the Gross-Neveu model. Of course, you can do it explicitly, integrating out the V variables, and you will get the metric of your sigma model eventually. So yeah, of course, nilpotent orbits, so on, they're very special varieties and so on. So this is not generic. No. It works for some models. But for example, dimensional reductions of gravity seem to lead to such sigma models. So dimensional reductions of gravity for some reason, give sigma models with complex target spaces. Not arbitrary sigma models, but they're homogeneous spaces and they're complex. And it should be possible to write them in this language, for example.
So what are you referring to? This dimensional reduction of gravity, like from 4D to 2D, or what?
Yeah, from 4D to 2D, but I think it also works from higher dimensions. So if you do from 4D to 2D, you get a SL2R over SO2 target space, which is a Lobachevsky plane, which is a complex one-dimensional variety. If you put gravity plus matter plus vector fields, you get something like projective space, but SU n minus 1 over SU n minus 1 times U1. So n is the number of so n is 2 plus number of vector fields. And this is like projective space, just with a Bergman ball or whatever. It's a projective space of negative curvature.
But it's a Euclidean space, or?
Yeah. It's it's a Riemannian space.
Yeah.
It's not. It's related to ADS in the same way as a CPN related to the sphere. Okay, just a negative curvature. So it's a complex analog of ADS.
CPN related to
the sphere of the corresponding dimension.
So it's basically ADS of Euclidean signature.
No. It's like I'm saying, it's like CPN related to the sphere. So ADS of ADS of Euclidean signature in my language, it's like a sphere.
Yeah.
Then there is another manifold, which is like CPN. CPN is not a sphere, right? It's a projective space.
Yeah.
You can have
it's a complex sphere, basically.
Yeah, in some sense, but it has different topology and so on, right? You could take an even dimensional sphere and you could take a CP of the relevant dimension. Alternatively, you can have this guy and you can have a Lobachevsky plane of same dimension. But they're not isometric. They are different. They have different metrics and so on. But yeah, this is a ball, a multi-dimensional ball in CN or something.
So the lower examples are not so helpful?
Well, the lower example is this, yes? So this is when n equals 2.
Yeah, that's the... And if it's just one vector field, n equal 3.
Then you have SU12 divided by. So this is two complex dimensional space. This is a ball in C4.
Mm.
In C2, I mean.
Oh, yeah.
So like model Z1 squared plus model Z2 squared, smaller than 1. This analog of Poincare disk, yeah.
Mm. That doesn't help for intuition, but yeah, this is interesting. I didn't know. I mean, I heard recently several statements about dimensional reduction of gravity having some extra symmetries that were not anticipated, but this one, yeah.
Yeah, this is just dimensional reductions of 4D to 2D of usual gravity with vector fields.
Mm-hmm.
So this is Bright and Lohner and Meson, I think. Yeah, and but I think it's also should also work from. I mean, all of this E8, whatever, E7, E6 target spaces that arise from higher dimension. I think they're also all complex homogeneous spaces. So complex symmetric spaces. Even. So I believe it's this is just the lower part of this tower. Kind of.
Yeah. So the model that you showed has, in terms of degrees of freedom, it describes basically a number of chiral scalars, right?
The beta gamma system describes chiral scalars, right? Then the interaction term couples them, right? The chiral left and right.
So the couplings are usually 2 left to 2 right.
Yeah.
So you cannot have different couplings, right?
Uh,
Just left self-interacting scalars.
Yeah. Self-interacting scalars. Well, I mean, yes. So J are always quadratic. Mm-hmm. So the J, the J currents for arbitrary quiver varieties and so on. The J's will always be quadratic combinations of the fields.
Mm-hmm.
J is a holomorphic one, so it corresponds to whatever left mover say.
Mm-hmm.
J bar is an anti-holomorphic one, so yeah, all couplings will be two left to two right. Well, why is that bad?
I'm not saying it's bad. I'm just curious about the fate of like just chiral systems. So having just left moving particles, can they interact?
Just left moving particles.
Yeah.
Yeah. So yeah, that's a good question. Actually, it's a good question because in principle, so here you see there's a funny fact that in the bosonic case, I wrote there is a current J equals U times V, right?
Mm-hmm.
But then there is this constraint that I also wrote before that V times U is 0.
Mm.
Remember, I wrote it right without monopoles. Yeah. So that means that J squared is 0.
Yeah.
By the way, this is the why relation to nilpotent orbits arises. I mean, these currents are 0 to some power. Some power of is 0.
Mm-hmm.
But the funny thing is that, for example, I think in SOSP sigma models, you have cases where J squared is non-zero, but J cubed is 0.
Mm-hmm.
So in principle, you could add something with J squared to the Lagrange. Yes. So maybe it's possible. In general, there is a idea that yes, maybe. So yeah, maybe this is not the full story. So it's true that maybe you can also add terms breaking, kind of changing complex structure, changing terms, like last kappa tilde trace J squared, let's say, plus kappa tilde bar trace J bar squared. Well, I mean, in these models, in the simplest cases, they will be identically zero terms. But in general, so it's known, for example, that deformations of these CPN models, if you want to have deformations, their metrics are not Hermitian. And that means that it's not just JJ bar. So JJ bar automatically leads to Hermitian metrics.
Yeah.
Hermitian on target space, yes. I mean, in the beginning we discussed Hermitian on worldsheet, but here I'm talking about Hermitian on target space. So they're not Hermitian. That means that probably this term should be present, but this has not been really worked out. So yeah, a priori. So these J currents, they are chiral invariants. So anything you can build out of these J currents is admissible.
But can you kill half of them, like put all the J bar 0 and then discuss only interactions that are in one chiral direction?
Well, as you see here, it would mean that it's just trivial, right? So
I mean, if you are adding the terms that come with J squared, if I mean you can do that in this system.
Maybe yeah, it's kind of hypothetical. Yeah, I think.
But then you also somehow,
if you don't insist on SUN symmetry, then you could add those terms. I mean, you could add like trace, whatever, A J squared, where A is some matrix. This would break SUN, but I mean, if you don't care about SUN, this does not break chirality or something. The point is that renormalizability requires that you cannot add J cubed or something. J has dimension 1, so you can only add J or J squared. So yeah, this would be some kind of, putting a matrix here would be some kind of deformation of this model. I think it's quite likely that some models like this, at least with mixed couplings, would be possible. Just has not been very much studied. But,
yeah.
I mean, it's known that a general metric, so on a general, say, complex manifold, when the metric is not Hermitian, you can decompose it into Hermitian part plus 2, 0 plus 0, 2 part. And if you do the first order formalism for that, you will get terms like this. So there is some hint that yes, it's a useful thing to think about, let's say.
And coming back to this J squared non-being 0, this reminds me of, I mean, from completely different direction. One can think of the quantization of the nilpotent orbits.
So
they correspond to higher spin algebras. And the case where your J squared is not 0 would correspond to partially massless higher spin algebras, I think.
So, these are non-minimal orbits, yes.
Right, yeah. So the minimal orbit would correspond to just when J squared is 0, but when you go a bit above, then you allow for a bit more possibilities. And yeah, that would correspond to the so-called partially massless higher spin algebras.
Yeah. By the way, so from these quiver representations, you can easily construct those oscillator representations for all of these generators. Yes, this is like quantum mechanics. You quantize this V becomes a derivative. If you go to, you can either use this constraint formulation where you impose a constraint on the wave function, like I had here, right? I use homogeneous coordinates. Then all generators are quadratic. It will be like a dagger A. But with these additional constraints, or I can go to inhomogeneous variables where I do not have constraints, but some generators will be cubic or something like.
All right, yeah. I mean, yeah. This is basically if you want to have manifest symmetry that's like with this homogeneous variables, then yeah, you have to sacrifice some. Yeah, there will be redundancy in your.
Yes. Here it's like going from homogeneous to inhomogeneous. And yes, if you want to work with homogeneous, you have constraints, or you can work with inhomogeneous. You will have this higher order.
Yeah, The constraint in this case is basically U1 constraint, right? And that is basically the there's some sort of duality that plays a role. So in the fixing this constraint in U1 somehow fixes what is the corresponding representation on the SUN side, or in a sense, what is the what are you quantizing? What is the orbit that you are quantizing? So I mean, also taking this constraint with some number, not zero, in general would be something very similar. It's just from physics, I guess you can interpret as monopole or whatever, but from this higher spin algebra perspective, this is just modifying your Moyal star product. Anyway,
okay, maybe we could discuss it and then separate.
Yes.
But yes, here the point is that the reason why we want to have non-minimal orbits is because, like I said, these nilpotent orbits, they're always singular, but they do not always have a resolution. And the cases when they do have resolutions are typically non-minimal. So the minimal orbits do not have resolution unless it's AN series. So only for SUN.
By resolution, what do you mean? Explicit solution for the constraint, or?
No. Resolution means some non-singular variety. So you have this nilpotent orbit, and then some non-singular variety, a map, some kind of projection, which outside of zero or outside of singularities is an isomorphism, but it replaces zero with some manifold. It's like exceptional divisor of the resolution. So in this case, it would be T star of G over H, what it glues into the singularity.
So you're saying that for the AN case, you have the resolution, which means that you have this manifold that it's some sort of a cone, right? So
what is a cone? Well, the orbit is a cone. The nilpotent orbit is a cone, but the resolution is not. Wow. Okay. Yeah. You mean a cone? Yeah. I guess it's correct. Yes. So on T star of G over H is there is a metric in principle that is asymptotically conical. Yes, that's correct. So yeah, the resolution looks like this, where you where here is an exceptional divisor. This is T star G over H. And then as you go to infinity, you stop seeing it. It just becomes, it's like a cone. Yeah, that's right. And the nilpotent orbit itself is a strict cone, where you just have a, you don't have this white waste here.
Yeah, that was the kind of reason why this manifold escaped the Gross-Neveu theorem, right? Of the that the star product is unique. Here you can add this monopole and you have different star product. They are not equivalent. The reason is that the manifold in the theorem, there is an assumption that the manifold has to be smooth. So, and the cone is not smooth. That's the
Okay. Yeah. Maybe later explain it. But yeah, so it's related. So this, so just the quantization of this. So in general, for an nilpotent orbit, what you have to do to get these representations, you look what quiver it corresponds to, and then quantize this quantum mechanics on that quiver, and it gives you these oscillator representations, like automatically. Well, you probably have constructed that.
Yeah, we can discuss that separately. I always wanted to understand the connection, but it's not that straightforward, but not that clear.
But you also studied the SO and SP cases, right?
Yeah, also SLM, yeah.
SLM, but also SO and SP cases.
Yeah. For SO and SP cases, it's yeah, there's no this deformation. So in case of SL, there is the deformation that we were just talking about. So maybe that's related to your statement that the resolution exists only for SL. But
yeah. And moreover, in cases where resolutions exist in NSO and SP cases, which are non-minimal,
yeah,
right? Non-minimal orbits can, some of them can. There's some classification which orbits can be resolved, some which, but I mean, when the resolutions exist, the resolved manifold is not a quiver variety. So the quiver is only for the singular case.
Oh, I see. Okay.
Except for AN. In AN, works both ways. So both resolved, unresolved. So yeah, it's some fine thing.
What is the advantage of having the resolution?
Here, my advantage for me is that I can relate those nilpotent orbits to sigma models.
Oh, I see.
And the other ones are not related to sigma models. You can just write some Gross-Neveu system, but it's not related to sigma models.
Oh, I see. So in that case, the Gross-Neveu is more like advantageous. You don't have a sigma model, but you have the Gross-Neveu model.
Yeah, more exactly, then you have, for example, interactions of the type not only modulus u squared, modulus v squared, but you have also u to the fourth plus v to the fourth. So you cannot integrate out the u and v variable to go to sigma model.
I see.
For general nilpotent orbits.
Okay.
You could, in principle, also study quiver varieties that are not related to nilpotent orbits also. So
yeah, I see. So the existence of resolution is somehow related to the fact whether this orbit is kind of discretely separated from the rest, or
yeah, it's related. Yeah, it's related. Yes, actually, I don't know exactly what's the sharp statement about it is, but yes, there is some notion of rigid orbit and non-rigid orbit. Yeah, and it seems to be in correspondence. So yeah, the rigid one does not allow a resolution, something like that.
Yeah, because this is the case for SOSP. It's unique, separated from rest. For SLN, it's a one-parameter family. So that probably
yes. But in principle, there are two different notions. So one is a deformation, the other is a resolution, right? So like in what you're talking about now is a deformation. When you so it's actually easy to see, right? So in SUN, you have, say, mu squared, j squared equals 0, but then you can replace it with j squared equals a.
Yes, yeah, this is the statement.
But in SO and SP cases, say you have j squared equals 0, but you cannot say that j squared equals a.
Right.
Because this just does not happen for these algebras. I mean, yeah.
Yeah. So that in the so SO case, at least there's a like oscillator realization that is simple to make the statement. So you have basically it's UV, but they have so you have basically three constraints, not one that is u dot v is 0, but three constraints, and there you have also u dot u and v dot v.
Yeah. That's in a minimal SO orbit. Yes.
Exactly. Yeah. So and this constraint you cannot deform this three constraints somehow.
Yeah. That is the so SOM. You have a minimal M minimal. It's the that's what I think we discussed with you at some point, right? It's n minus 3, and the one corresponding to or maybe two n minus 3, right? So maybe two n minus 3. Is it 2 n minus 3, right? Yeah, and the one that corresponds to the T star of the relevant relevant homogeneous space, which is SO2 times SON minus 2, is 2 times n minus 2. And that corresponds to you drop one of those constraints. Like you say V, drop one of the constraints, one of the off-diagonal constraints. So
yeah, so these three constraints form SP2 algebra. So in the hot duality sense, you have dual algebra SP2, where you have to choose a representation of this SP2. Of course, it's only the trivial representation that has all the generators act trivially. You choose different representations, then you have to change these constraints, yes. So naively, there is this deformation where you, for example, choose a finite dimensional representation of this SP2. That would correspond to so your algebra will increase on the other side. So so you would have a same dimension probably as the minimal one, but is it true? But you add a discrete dimension in the sense that you have several. So in a sense, as like SP2 finite dimensional representation compared to 0-dimensional one, it just has finitely many states, right? So in the sense that it doesn't have a full one new dimension, continuous dimension. So there you get an orbit which is like several 2n-3 dimensional orbits stacked together. This is a new orbit. And the next would come the case where you, for example, take so from the representation point of view, this can be understood as for SO 2, n or 2, n-2, which is a conformal algebra in n-2 dimensions. So you can think of this as like conformal fields in n-2 dimensions are the minimal orbit and then next to minimal and so on. They describe some conformal fields there. So naively, you start from box phi equal to 0 equation, the simplest conformal scalar, that would correspond to the minimal orbit. You take box squared phi equal to 0, that would be this new ones that come, because that will be discretely more number of scalars, right? You have basically two scalars as box squared phi. So, but if you want to jump into the other dimensional orbits, then they become the ADS fields in one higher dimension. So this is somehow structure. So if you take a product of two minimal representations, which correspond to this minimal orbits, then that gives you spectrum of Vasiliev theory in ADS. So all the massless higher spins. This is Plato-Fronsdal theory.
But I mean, the SO and SP, what do they correspond to in place of SLN?
So the SO, we usually, we are interested in case of SO for the higher spin algebras because we interpret SO as the ADS algebra. So SO 2, T is the T plus 1 dimensional ADS algebra. And there, the minimal representation of it is the conformal field living in the boundary. In the field theoretical sense, yeah. So, yeah. SP is a bit different. I mean, the
or a cell. I mean, what do they?
For example, so SLN is interesting only in cases where there's isomorphism with the SO. So we have the SL2R is isomorphic to SO 1, 2, right? Then it is kind of ADS2. Then there is the SL2C, which is de Sitter in 3 dimensions or stuff like this. So SL4 is isomorphic to SO6 or SO 2, 4.
Yeah, but I mean the ones that are not isomorphic. Can you take?
We have no physics associated with it. I mean, from a higher spin perspective.
So it's just the lower dimensional groups that have some physics interpretation.
Yeah, I mean, it was just this SL4 as SO6. There was some interesting stuff that with Ruben, actually, I don't know, he probably left. With Ruben, we had this work where we kind of used this SL4 versus SO6 to kind of show that there is a one parameter family of algebras in 5D ADS, so for higher spins, which was kind of a shocking discovery at the time. But the interpretation eventually that we came up with later working on the higher spin algebras with Tejan was that it is just because for SLN it is always the case. You have one parameter family of minimal representation. While because of these isomorphisms, in cases where you have this isomorphism with SLN algebras, so it's basically 2, 3, and 5-dimensional ADS spaces. You have one parameter family of higher spin algebras, and this was known for 3D. The 5D was our discovery, then we constructed also the structure constants and stuff. So yeah, the SLN, it was just a interesting thing we just generalized, but naively the interest for the studying these algebras came from SO cases only.
Okay. And here it's kind of the contrary, because so the CPN model is like very well known model, and the SOSP sigma models are like exotic. So I mean, no one has studied carefully or anything. So here.
Yeah, but I'm wondering if anyone ever needs these algebras that correspond to the symmetries of this principle, the minimal representation for corresponding to this nilpotent orbit that is minimal. We had like some non-trivial computations of the coupling constants for these algebras. I'm not sure if people are using this stuff. For some cases, there were some works where people are computing SL2Ks and stuff. They would take some things, but generally, this application of this mathematics I haven't seen anywhere, but it would be natural in this context.
Yeah, and I should also say there is a lot of this nilpotent orbit stuff in 3-dimensional supersymmetric theories, right? Dimensional reductions of n equals 2 to 3 dimensions. There is this mirror symmetry. So, I mean, there is a lot of kind of bunch of work on this nilpotent orbits by Hanani et al. So actually we borrowed some explicit examples from his work, because I mean he worked out he summarized some salient examples more concretely than what is done in the math literature. So there it arises as some Higgs branches of some field theories. So some minima of the potential give these nilpotent orbits. In Hanani with maybe Nopadol and so on. We have done some stuff. I mean, Hanani certainly has a bunch of work about that.